The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm Rochelle Saunders, guest hosting today for Desiree Shell. This week we're talking about stars and how the study of the universe is progressing right here on Earth. A little later, I'll be speaking to astrophysicist Ethan Siegel about an interesting quirk of physics involving black holes. And astronomer and science communicator Pamela Gay will join us to talk about how changing funding models in the U.S. are affecting ongoing research. But first, let's learn about how we may be able to study ancient supernova by looking at evidence from the ocean floor. Our first guest today is Jennifer Ouellette, the author of 4 popular science books for the general public, the most recent one being The Calculus Diaries: How Math Can Help You Lose Weight, Win in Vegas, and Survive a Zombie Outbreak. She blogs at Cocktail Party Physics at scientificamerican.com, and one of the posts on that lovely blog is why she's here today. Great to have you back, Jennifer.
Oh, thanks very much.
Now, the post you wrote was about the evidence for a supernova found in an unexpected place. Can you walk us through that?
It's basically, we would like to tie evidence for a supernova event at a specific time to evidence here on Earth. And what this guy has done, it's a German scientist named Sean Bishop, is he has looked for a very specific radioactive isotope that would not normally be found on Earth, and he's found traces of it in the crystals left behind in these little microfossils from these magnetotactic bacteria that live along the ocean floor. It's really quite an ingenious way to search for this sorts of things. Back in 2004, a bunch of scientists thought they'd found evidence of this isotope. It's called iron-60. It's really not normally found on Earth anywhere at all. So if you find it anywhere on Earth, that's generally evidence for a supernova, because most of these sorts of elements need those sorts of the high energies of a supernova to form. But that particular paper was kind of debatable. There were questions raised about the methodology, about whether their analysis really was accurate enough. So they wanted to find a new way to test for the same trace, and Bishop came up with this ingenious way of doing it.
So, for the people who aren't aware, what actually causes a supernova?
Oh, well, this is what happens. You have a very large star. Most smaller stars like our sun are not going to go supernova. But once you reach a certain limit, once you surpass a certain limit in terms of mass, what happens is the stars burn through their fuel over billions and billions of years. And at some point, as they move from hydrogen to helium to carbon and oxygen and so forth, there's nothing left but these heavier elements, iron and nickel, and they're heavy enough that the cores collapse and the stars explode into supernova. And that's why we have any heavy elements at all. That's why we have platinum. It's why we have gold. That's why we have uranium. Because in order to get these heavier elements, atomic nuclei need to fuse, and you need huge amounts of energy. You need the energy of a supernova. So they essentially become these furnaces, that form these heavy elements.
So why is iron-60 so rare?
It's radioactive, and it happens to have a very short half-life, which means that, once the supernova explodes and it scatters these elements throughout space, as it travels through space, it's slowly radiating away and turning from this isotope iron-60 back into regular iron. And by the time it gets to our solar system, there's just nothing left most of the time. I mean, our solar system compared to your average star is not that old. So it just isn't found. It doesn't form naturally. And so any trace that we can find on Earth is generally going to be evidence that at some point we were close enough to a supernova not to, say, get burned up, but enough so that this element could find its way through our atmosphere down to the ocean floor.
So while the idea that evidence for a supernova could be found in these bacteria, the bacteria themselves aren't exactly a new discovery, are they?
No, they've been around. They've been known since like the 1970s. They're called magnetotactic bacteria because they navigate by sensing magnetic fields. And they do this by forming these crystal chains in their bodies. And they essentially suck up iron and iron isotopes like iron-60, if it's present. And it forms these little chains. And through those chains are sensitive to magnetic fields. And the bacteria then use these to navigate. And then the bacteria die, and those chains end up in the ocean floor sediment. So what Sean Bishop has done is take these core samples, isolate the iron and the iron 60 by using various chemical processes that he's developed over several years, and then measured to find evidence of, at what points would you get these spikes of iron 60. And basically there's evidence that about 2.2 million years ago, there was a supernova, probably in Scorpio Centauri, that seems to correspond with the time in which this signature is popping up.
So this supernova, I guess, would have been at a distance that was far enough so as not to incinerate the Earth, but close enough that the extremely radioactive iron 60 would actually hit the Earth.
Right. It would last long enough to make its way slowly through the Earth's atmosphere and get distributed along the ocean floor.
So do we know why these bacteria have this ability to navigate with, I guess, magnetism?
They sense magnetic fields. We don't know why they do this. This is clearly a very ingenious evolutionary skill that they have developed probably over billions of years. But they make use of the natural iron in their environment in the ocean water. That they like low oxygen environments. They don't like a lot of oxygen in their environment. So they try and find those. And what happens is they're able to sense the magnetic fields, and that tells them which direction to go to get to these low oxygen places like the bottom of the ocean.
I believe Mr. Bishop is actually still looking for more of this iron 60, correct?
Right. I mean, this was at a meeting of the American Physical Society like a week or so ago, and he was very careful to say these are preliminary results, but they're very promising, and he actually thinks that once it goes through peer review and he does all his double checking, that this result will hold up, and we should know in the next 6 or 7 months. There's another isotope that he hopes to test for next called aluminum-26. Similar sort of thing, that also should be there in abundance. And if it shows up in exactly the same or roughly the same time periods, then I think that you could say that's a pretty convincing smoking gun. It's just such a cool idea. Like I said, I mean, it's a preliminary result, so you don't want to get too excited, but it's ingenious that we could think about something that a star explodes 2.2 million years ago, and we can, now today find evidence of it in these little bacteria, remnants of bacteria, these little microfossils.
I believe he's actually got to go through quite a lot of painstaking searching to find these iron 60 atoms. I've heard that he has to sort of sift through and basically look for them one by one.
He is looking for them one by one, and that's why it's such a tough measurement to do, and that's why he emphasizes that these are preliminary results, because there aren't very many. The spikes that he's talking about are not huge. It's not a huge amount of iron 60, but the fact that there's any at all is significant. And now the question is he misreading it in some way? Is this a false signal that showed up? Is it a statistical artifact? There's lots of reasons why this result might not bear out. But evidence has been found, roughly 10 years ago, and even though that methodology may have been so-so, the fact that we've got another line of evidence, a new way of measuring for the same thing, and we're also seeing evidence of iron 60 being in the sediment along the ocean shore. Now we're starting to see some evidence accumulating. To me, that's when you start thinking, there might be something interesting going on here.
Since you're here, a little bird told me that you're actually working on a new book. Is that correct?
Yes, I am. I've turned it in. It's going through the whole production and copy editing phase as we speak.
Can you tell us what it's about?
Yeah, it's called Me, Myself, and Why. The working subtitle that will probably change is Searching for the Science of Self. I became interested in this question when I was working on the calculus diaries. I realized that somehow I had formed this personal identity, this view of myself where I was bad at math, and then I realized that actually was not the case. And it got me thinking about the ways in which we form personal identity and the stories that we tell ourselves, that we construct about who we are and what we can and cannot do. And it ends up influencing the choices that we make sometimes. So I ended up getting my genotype done. I got my brain scanned. I took a bunch of personality tests just to kind of explore that. I dropped acid, believe it or not, because that sort of dissolves the self-other boundary. The irony of that being that I just don't do drugs. I'm not that person. I hate drugs. They just don't do anything for me. I find them boring. But acid was a really kind of interesting experience because there's still an I, there's still an ego, you're still conscious and present, but your body dissolves and you just kind of end up being a bunch of molecules kind of floating with all the other molecules. And there's some very interesting things going on in the brain that nobody has yet really had a chance to study, because LSD, it's just very hard to get that to get the substance itself for these scientific studies. But it was a really intriguing experiment to do, and it ended up being a nice lead into a whole chapter on consciousness and the soul and the whole mind-body dichotomy.
So this sounds like it was really as much a personal journey for you.
Yeah, it's probably the most personal book that I've written. I've always sort of woven in, beginning with the Calculus Diaries, there was a little bit of personal stories there in the blog. Certainly, there's definitely an I in the blog. This was the first time where I really, ended up drawing anecdotes and things very much from my own life. And it ended up being kind of a really interesting personal journey.
So when should we expect your book to come out then?
Well, it's looking right now to be January, February of 2014. So I will definitely keep you all posted. We'll see. I mean, I'm actually very excited about it. It's a very different book for me. Normally, I focus on physics and mathematics, and this required me to delve into genetics and neuroscience and social and cognitive psychology and things that are actually very challenging to write about. I was kind of longing to get back to physics where there's a right and wrong answer.
That is sometimes one of the nice things about science, is sometimes there is a yes and a no.
Exactly.
And not a maybe. Jennifer, thanks for being here, and we will wait as patiently as we can for 2014.
Great. Thanks very much.
You can find Jennifer Ouellette at Cocktail Party Physics on our website at skepticallyspeaking.com. And we'll be back with theoretical astrophysicist Ethan Siegel, who I'll be talking to about the black hole firewall paradox, right here on Skeptically Speaking.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
I'm Rochelle Saunders, guest hosting today for regular host Desiree Schell. I'm here with Ethan Siegel, theoretical astrophysicist and professor at the University of Portland and Lewis and Clark College in Portland, Oregon. He has previously taught at the University of Wisconsin and done astrophysics research at the University of Arizona. He maintains the excellent science blog Starts With a Bang on the Science Blogs Network, where he writes regularly and passionately about the universe. It's great to have you back, Ethan.
Yeah, it's my pleasure to be back. Thanks so much for having me, Rochelle.
Okay, so a little over a year ago, a string theorist named Joseph Polchinski, and I'm sure I just completely mispronounced that name.
You nailed it.
Awesome.
Nailed it.
But he was contemplating what would happen to a hypothetical astronaut who dived into a black hole. And it seems to have created quite a stir in the physics community. Can you tell us why?
Well, we have two things going on here. One is we have our laws of gravity, right? That's general relativity. That's Einstein's theory of gravity. This tells us how space-time works on the largest scales. It tells us how black holes work. It tells us how gravity works. It's our most successful theory of the universe of all time. And every time we've run it up against new observations, it's come through. It's been spectacular. On the other hand, we also have quantum mechanics. That's our theory of all the particles in the universe, of matter, of energy, how every object in the world exists and interacts with one another. But these two theories aren't compatible with each other. General relativity isn't a quantum theory of gravity, and we don't have, in quantum field theory or quantum mechanics, any way to account for gravity or for curved space-time in general. So whenever we have problems that involve the marriage of these two things, we're on the lookout for paradoxes, because when we find these places where these two types of frameworks for the universe conflict with each other, that's our chance to learn something new about the universe.
So why is the firewall idea so controversial?
Well, here's what happens. If you get close to a black hole, we can tell you with absolute certainty from general relativity and from quantum field theory what happens outside of the event horizon of that black hole. Our laws of physics are on solid ground there, and as long as we can do our quantum field theory in the curved space-time outside of the black hole, we are in great shape. The problem happens if you think about it like this. Imagine that you and I are two particles outside the black hole, and we know about each other. We can interact with each other, we can exchange information, we can talk to each other. We know what's going on with you and I as long as we're both outside the black hole. Now, let's say I go and take a trip inside the event horizon of the black hole. Well, now there's a problem, because you're outside the black hole. And once I cross inside so that I'm in the black hole, nothing I can do can get out of that black hole, right? That's why it's called a black hole, because nothing, not even something moving at the speed of light, would be moving fast enough to escape. And that includes, as far as we understand it, any information. So as long as I do something when I'm outside the black hole, you can know about it. But if I do something once I'm inside the black hole, you can't. Now, in quantum physics, two particles can be what we call entangled, which means that, let's say you and I can have a total spin of 0. Well, you can be spin plus a half and I can be spin minus a half. And if you measure my spin, you immediately know what your spin is because it has to sum to 0. But what if I fall into the black hole and then someone measures your spin? Well, presumably now they would know something about my spin, but they shouldn't be able to know any information about me because I'm inside the black hole. So that's sort of the root of where this paradox comes from, is that you're learning information about me, but you shouldn't have any right to know information about me because I'm inside the black hole. So what happens is, according to this firewall problem, if you have two entangled objects, like you and me outside a black hole, and one of them goes inside the black hole, how does information get exchanged across that boundary? So according to this firewall paradox, when you make a measurement like that, some sort of information has to be exchanged. The way we typically do that is through photons, but the event horizon of the black hole, the edge of this black hole, the boundary between where information can and cannot escape from it, the way this firewall paradox comes about is it says, well, we're going to create a photon here at the boundary of the black hole. Now, black holes exist for billions of years in the universe, and so when enough things have fallen in and enough things haven't fallen in, what this means is over the history of the universe, this entire event horizon of the black hole should by this point act like a giant firewall. This is also because time is frozen at the event horizon of the black hole. To someone falling in, they would get fried by the photons that exist there. So that's where this problem, this paradox of a black hole firewall comes from. It comes from trying to reconcile what we know about quantum mechanics, quantum field theory that interacts between all the particles in the universe, and also between general relativity that sets up this event horizon boundary between what's inside a black hole and the outside universe that we live in.
Let's just keep going with the idea that the firewall does exist, because it sounds like if the firewall does exist, then relativity could be in a lot of trouble. How much trouble could Einstein's theory actually be in if the firewall is in fact there?
Well, you know, the nice thing about relativity is we have tested it in a whole slew of different ways, right? We've tested how mass bends light in the universe, and we know that to remarkable precision. We've tested how the path of a photon would actually get time delayed from passing near a gravitational mass. And that's why we can make our GPS satellites work. If we didn't know about general relativity, every single position from a GPS satellite would be off by about 30 meters. But because we know how general relativity works, there's no problem. We've measured how objects in a strong gravitational field, such as Mercury orbiting the sun, has its orbit perturbed by the sun. We've measured how two spiraling neutron stars will actually lose energy and their orbits will start to decay. In theory, there are gravitational waves out there in the universe. If we could detect them, that would be another confirmation of general relativity. Every time our technology has progressed to the point where we've been able to make a new test of general relativity, it's been vindicated, it's been validated. Einstein's theory hasn't failed us once. But one thing, like I said, we don't know about yet is how does gravity work at the quantum level? There really hasn't been a way to test this yet, but it seems like our notion of quantum field theory and how particles interact and general relativity, they can't both be right if the firewall is there. General relativity should not allow this stable firewall to exist. There's something called an innermost stable circular orbit in general relativity. Relativists call this ISCO because that's the acronym for it, innermost stable circular orbit. This occurs well outside of the event horizon. In general relativity, any photon, any particle at all that's created inside of ISCO or closer to the black hole than that is doomed. It will eventually spiral into the black hole, fall in past the event horizon, and head as quickly as it can towards the singularity at the center. But if this firewall is there, it tends to make us think like, wow, we've got this eternally stretched thing across time that's going to be this firewall at the event horizon. And general relativity really doesn't allow you to have that. So either quantum field theory, quantum mechanics, this prediction is flawed, which is interesting. General relativity is flawed, which is also interesting. Or there's a resolution to this paradox. Quantum mechanics is right, general relativity is right, and the firewall is somehow forbidden from existing.
So you talk about that relativity is a very well-tested and sort of secure part of our physical theory. And I believe quantum mechanics and quantum field theory is also one of the most tested theories that we have in science, which is why we use it for so much. Would you say they're sort of on equal footing as these pillars?
You know, it depends on who you ask. From my perspective, there are ways that both of these theories are incomplete. For example, we can describe all the particles and all the known interactions in the universe with quantum field theory as we currently understand it. But it doesn't explain everything. For instance, it doesn't explain gravity. It doesn't explain certain particle properties. It doesn't explain why certain types of decays in nature don't occur. It doesn't explain why you know about the Standard Model, all the elementary particles, and why they have mass. The Higgs boson and the Higgs mechanism gives them mass, and it tells us why we have mass. But quantum field theory, as we understand it, doesn't tell us why these particles have the mass that they do. It doesn't tell us why neutrinos have mass instead of being massless. It doesn't tell us why, when we have certain types of decays, it doesn't tell us why certain quantities like charge parity violation doesn't occur in the strong interactions. So I would say that quantum mechanics, quantum field theory is tremendously successful for the things it does predict, but there are certain things that we don't see in the universe, or we do see in the universe, that quantum field theory and quantum mechanics at this point doesn't predict. And the same thing is true for general relativity. General relativity, for everything we've been able to test it for, it's absolutely successful. But there are certain things where general relativity is no good at making predictions. For instance, if you ask what happens at the singularity inside of a black hole, general relativity breaks down. It doesn't tell you anything sensible. It gives you things like infinity as an answer, or 1/0 as an answer. It gives you undefined mathematical quantities that don't make sense. And so I suppose it's fair to say that as far as they've been tested, general relativity and quantum field theory both are absolutely impeccable for our understanding of the universe. But there's no way this can be the absolute final fundamental theories of everything because they don't explain everything that we can imagine.
This is Skeptically Speaking, hosted today by Rochelle Saunders. I'm speaking with astrophysicist and science blogger Ethan Siegel about the recent black hole firewall paradox that's been making headlines in recent weeks. So this isn't the only time relativity and quantum mechanics haven't played nicely together, though, is it? I mean, there have been other paradoxes prior to this one.
It's very convenient to sort of frame it as this tension between relativity and quantum mechanics, but in reality, we have approximations that we use that turn out to be incredibly successful for almost everything in the universe. For instance, as long as you're outside of a black hole, space-time is curved by such a small amount in general relativity that we can approximate space as being completely flat and still get excellent results using quantum field theory. The problems arise when we start to do quantum field theory in strongly curved space-time. There's this feedback problem that if you want to know what your space-time looks like, you need to use general relativity to get that. But all the matter and energy, including all the particles, all the photons in the universe, they're what determines the curvature of space-time. So as far as things practically go, general relativity can be used to determine what does my space-time look like, and then you can take the shape of that space-time, do your quantum field theory calculations, and get a sensible answer under almost all conditions. But it's fun theoretically to think about what are some conditions when you get that will give you answers that don't make sense or that aren't the thing you expect to get out. If we can find places where general relativity and quantum field theory aren't playing nice with each other, that's where we really get an opportunity to learn some new physics. There have been paradoxes in the past, but we've appeared to resolve those. One of my favorite ones was, classically, according to general relativity, nothing can escape from a black hole. But when you combine general relativity and quantum mechanics, you can get something escaping from a black hole. This was shown in 1974 by Stephen Hawking, and it's named Hawking radiation. The way this works is because of quantum mechanics, quantum field theory, the vacuum, what we think of as absolutely empty space, something with no matter, no energy, no particles in it, turns out to not be completely empty. There is an energy-time uncertainty relationship, which means if you look at a region of space-time for a short enough time, there can be an inherent amount of energy in that region of space-time. In terms of particles, you can have particle-antiparticle pairs that pop into existence for a brief amount of time and then immediately annihilate each other again and disappear from the universe. But if they happen to be there when you're looking at them, boy, empty space really isn't empty anymore. This paradox arose near the event horizon of the black hole. They said, what happens if you make a particle-antiparticle pair so close to the event horizon of a black hole that one part of the pair, either the particle or the antiparticle, actually falls into the event horizon, but the other one doesn't? This is a paradox because if one of them falls into the black hole and the other one escapes from the black hole, then these particles can't annihilate each other anymore. They won't find each other. One will get sucked into the black hole. The other one can get accelerated and spit out of the black hole. But all of a sudden, what you've gone and done now is you've got a black hole that you've learned nothing can escape from, and now I have either a particle or an antiparticle coming from near the event horizon of the black hole. well, what's going on there? It shouldn't be happening. And moreover, if energy is conserved in our universe, what's happening to the black hole? How did it make this particle come from nothing right outside the black hole? Well, the resolution of this is that the particle that gets emitted from the black hole will have positive energy. The one that falls into the black hole in order to conserve everything will actually come in with negative energy. So when it reaches the singularity at the center of the black hole, that black hole will lose mass. This is something that can only be resolved by using quantum field theory in curved spacetime. It turns out when we were able to do that successfully that there was no paradox there, that in fact Hawking radiation was actually the thing that was calculated, including the spectrum, how much energy should be in the particles that are emitted right outside this black hole. So that was a case where when you looked at it naively or originally, we thought that there was this inherent tension between quantum field theory and general relativity. But when we were able to successfully do the calculations, we were able to find that no, in fact, this is exactly what's predicted.
So I actually heard that there was a paper released fairly recently, I think in the beginning of March, that actually may have resolved this firewall paradox.
So you and I have just talked about quantum entanglement, right? We imagined what happens if you and I are entangled in this way that you have intrinsic properties, I have intrinsic properties, but in a very Schrodinger's cat sense, unless you measure one of our properties, you don't know what they are. You know, you could be spin up and I can be spin down, or you could be spin down and I can be spin up. We can't both be spin up and we can't both be spin down, but unless you measure one of our spins, we're both in a superposition of you're some percentage spin up and some percentage spin down, and I'm some percentage spin down and some percentage spin up. It's only when one of us is measured that we both have our spin state determined. So this is what's called entanglement. When you make the measurement, the entanglement is now broken, because now your thing is determined, my thing is also determined. We're not entangled that same way anymore. If that's what's going on, if you have a certain level of entanglement, what that does is the more entanglement you have, the later the curtain falls on the firewall. So if there were no entanglement at all, or a minimal amount of entanglement, then once you cross the event horizon, the firewall would be immediate. But it turns out that entanglement of particles in the universe, it seems to be rather large. And what the paper that was published in Physical Review Letters showed is that you have all these particles in the universe, and they're entangled with one another in, a variety of ways. What the paper showed is that if entanglement between particles in the universe is maximum, that is, based on the interactions that happen in the universe over its history, entanglement could have any number of values. There's a wide range of values they could have. But if the entanglement between particles in the universe is maximized, in other words, if looking at the entire way that the whole quantum system of the universe interacts with itself, if there's no possible way to have a greater level of entanglement, then the amount of time it takes for this firewall curtain to fall is not only maximized, it's actually pushed out farther and farther and farther the more entanglement you have. And if you have the largest amount of entanglement possible, what this paper showed is that the firewall does not fall until an infinite amount of time has passed. And because the universe is not infinite in time, thanks to the results from Planck, we have a better refinement that the age of the universe is actually 13.8 billion years old, which is old, but is infinitely shorter than an infinite amount of time. that means there never will be a firewall.
Infinities always seem to cause so much problem in physics.
I try to use infinities for good rather than for evil. And if we can use infinities to show that, hey, you know what, this tension here, this thing that quantum field theory says should happen that would be wrong for general relativity, if infinity is something that tells us, hey, this won't happen in a finite amount of time, then it's not relevant for our universe, and both quantum field theory and general relativity are still safe.
So I'm curious, is this paradox more of a kind of mind mathematical problem, really kind of abstract mathematical problem, or are there actual real physical things that this could affect this kind of paradox?
You know, one of the things people think about here is this is really sort of the ultimate type of encryption, right? If you and I share a code and we don't want anyone else to have the key to this code, you can have a set of systems. We can make two systems that are quantum mechanically entangled. And if you take one and you go in one direction and I take the other and I go in the other direction, well, if one of these systems is the key, then the other one can also be the key. But only you and I have this information. If you make your measurement, you have the code. And then, because you made your measurement, I also have the code. Because whatever your entangled system tells you, mine is directly tied to that. And so you might say, hey, we can really do the ultimate encryption where we can make a system, we have a code, and you and I are the only two people with the key because we're the only two people who have the quantum mechanically entangled system. I can go into a black hole, presumably. You can break the entanglement, you can make the measurements on your system, and now, even though there's a black hole separating us, even though there's an event horizon there where nothing can get out, I still have the broken entangled system, because that black hole event horizon doesn't prevent quantum mechanics from happening like that. This is not something that general relativity will stop from occurring. There's no information being transmitted there. We would never know that this entanglement was broken unless you and I came back together after we broke the entanglement and compared our systems.
Ethan, thank you so much for joining me today, and come back anytime that there is a new development on the frontier of physics.
It's my pleasure. Thank you for having me, and thank you for sharing this story with the world.
If you want to learn more about Ethan Siegel or the latest in physics research, you can visit his blog at scienceblogs.com/startswithabang, a link you'll be able to find at our website skepticallyspeaking.com in our show notes. And we'll be right back with astronomer and podcaster Pamela Gay to discuss the changing landscape of science funding in the U.S. right after this.
On the next episode of Skeptically Speaking, we're looking at birds and what the study of their behavior and anatomy can tell us about ourselves. We'll talk to Dr. John Marsloff, professor of avian social ecology and demography at the University of Washington, about his book, Gifts of the Crow, How Perception, Emotion, and Thought Allow Smart Birds to Behave Like Humans. And we'll speak to artist and illustrator Katrina Van Grauw about The Unfeathered Bird, her book that looks at bird anatomy below the feathery surface. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Next, we're speaking with Dr. Pamela Gay. Pamela is an astronomer, writer, and podcaster who focuses on using new media to engage people in science and technology. She is the director of CosmoQuest, where people can both learn and do science, and is a co-host of the most excellent podcast, Astronomy Cast. She also maintains the blog Starstrider. Welcome to the show, Pamela.
Thank you so much for having me.
So tell us about CosmoQuest. What does it do and who does it benefit?
We are an online research facility that works to engage the public in helping scientists working with a variety of different NASA missions accomplish research tasks they otherwise wouldn't have the manpower to do. It's really quite amazing what an everyday person can do if they just have 10 minutes alone at their keyboard.
So is this kind of leveraging the citizen science point of view?
That's exactly what this is. It's a citizen science site, but it also goes on to add all the other things that we researchers enjoy at our universities. We have seminars, we have virtual star parties, we have classes that people can sign up for. So at its core, we're crowdsourcing discovery of our universe. We're doing citizen science, but we're not just asking people to be click workers, we're asking them to be our collaborators in every sense of the word.
That sounds pretty cool. So people who are involved in CosmoQuest, do they actually get to work on NASA problems?
Yes, that's exactly what we're doing. We currently have 3 different projects up and a 4th one launching soon, where we're exploring the surfaces of the Earth's moon, the asteroid Vesta, and the planet Mercury. And we have a variety of different science tasks that our science teams want answered. We're trying to find where are the boulders, because that's an excellent place to go send a robot to collect a sample, because when you see a boulder on one of these other rocky surfaces, that's actually a piece of bedrock that was dug up during an asteroid impact. We're measuring where the craters are, trying to understand the geologic history. We're looking for craters that have specific collapsed walls that indicate that the sediments that made up the surface are made up of a variety of different densities. It doesn't sound all that exciting, we're mapping craters, but we're actually getting ready to rediscover the age of the Apollo region by recounting the craters there. And we're looking to try and understand how shaking and rattling the moon when it gets hit actually works to erase the moon's past by erasing small craters.
So how does this work from the perspective of someone who logs on and wants to help? Do they look at photos? Do they look at what sort of data are they looking at?
We're looking at for the moon images that are at such a high resolution that if you're standard tall male were to lay down on the surface of the moon and assume the snow angel position, you could actually make them out in the images. So these are extremely high resolution images, roughly 0.5 meter per pixel resolution. And people are looking at these in a standard interface that is familiar to anyone who's ever used PowerPoint's drawing tools. And we're getting people to use those drawing tools to mark where are the craters, to put little X's marking where boulders are, and to flag with little markers that look kind of like Google Map markers where are there interesting things for our science team to go follow up.
So how much background in science do you need to participate in some of the things on CosmoQuest?
Absolutely none. Really, all you need to be able to do is have basic pattern matching skills. You need to be able to recognize this circular thing. This is what I was trained is what a crater looks like. We have a tutorial that we provide to give you the basic understanding of this is what you mark. And then beyond that, we have all sorts of detailed geological information that people can learn from on the site. So to get engaged, we've basically learned all you need is to have the skill that when I say mark a crater, instead of drawing a giant circle around the outside of a crater, which is what little kids do. You need to be able to mark on the edge of the crater, basically stay within the lines. If you can do that, you can accomplish our primary science tasks. Understanding it takes longer, and we hope that everyone will do that extra reading to understand the science they're helping us accomplish. But getting engaged, it's 5 minutes to register, get started, and complete your first few images. I actually find that I can work on this stuff while my husband's watching things like Duck Dynasty on television. I'm not sure why he likes to watch Duck Dynasty, but I can just sort of go, yes, honey, and sit there and play in the interface. And it feels like play, but it's actually doing science.
That sounds really awesome. What other kinds of programs, you mentioned educational programs, is CosmoQuest involved in?
Beyond just doing the citizen science, we're also getting people involved in learning science. We have a variety of different series ranging from every Monday we do Astronomy Cast live through a Google Hangout on air and then record it for an edited version to come out in podcast form later. Wednesdays, we do sessions on here are the different educational programs available all across the world. Thursdays, the Planetary Society, which is one of our collaborators, does a news show on something new out of planetary science. Friday, we do a roundup of all the latest news coming out of astronomy and space science. And then every Sunday night, we do something that's kind of special. We do what we call our virtual star parties. And this isn't like what you see with SLU and some of the others where it's a formal telescope and a formal professional giving you a lecture on what's being seen. We get a bunch of just everyday people who have amazing backyard telescopes that are their passion. And they show us the sky through their eyepieces, through their cameras. And we bring in some professional astronomers, myself. We have a fellow named Thad, Astro Thad, out in California. Nicole Gallucci, noisy astronomer, joins us, and we try and do the color commentary to these images that are coming in, and it's just fun, and we work to recreate that out in the dark at night, laughing with friends while looking through eyepieces experience of a real star party.
So it sounds like a lot of the work you do with CosmoQuest is really kind of online new media tools that opens it up to people sort of beyond your local community.
It's reached the point with modern technology that, well, if you don't want to, you really don't have to leave your house. Amazon will even bring you food. I don't advocate for becoming a hermit, but when it comes to trying to reach out and find those other people out there who love science, it's sometimes hard to do. And living here in rural America, I find it easier to find cows than to find people with telescopes. Reaching out to people across the internet, it's a way for me to find community and to help others find community of like-minded, curious people who just want to help explore our cosmos. It can all be done online. We should go out and meet in the real world, or meet space, as I've often heard it called. But you can start building those connections in the virtual world and use those virtual worlds to learn, to explore, and to collaborate.
The internet is really a wonderful thing.
It really is. I can't imagine how so much got accomplished without it. I couldn't have done what I do without the internet.
So, Pamela, recently you wrote a post about how your program and others like it are being affected by funding cuts. Can you tell us that story?
I don't think a lot of people realize what's going on because of the spin that's being shown in the media. The Office of Management and Budgets is the organization in the U.S. government that does all the distributing of money, and they work directly under the White House. And they have been pointing out for several years that funding that goes to science education goes to a myriad of different agencies. You have people at the National Institutes of Health that are working to do public health education, which is a form of science. You have people at DARPA running science and engineering campaigns to build remote control cars. You have people at NASA doing projects like mine that engage people in doing science and train teachers and help get kids involved in understanding the latest results coming from all of these different NASA spacecraft we have out there. Well, in the world of managing finance, it's awkward to have educational funding distributed to all of these different otherwise known as science agencies. And so the decision was made in this year's White House budget to consolidate all educational funding under the Department of Education, the National Science Foundation for Educational Research, and the Smithsonian Institutes for Outreach. And that's an awkward situation for us to be in, where those of us who are scientists and science communicators, well, half of us just got amputated and sent to a new part of the government we've never worked with, we don't know how to work with, and there aren't any funding calls out there. So we're being told to prepare to potentially have our funding zeroed by fiscal year 14, and we don't know where the money's going to come from. We're looking at all the experts in science education working for NASA and the other science-focused agencies in the U.S. government losing their jobs. And what we're seeing in the news is people saying that the latest budget gives several $1 billion to STEM education. Well, yes, it does, but it does that at the cost of removing STEM education from other parts of the government.
So is this actually a matter of funding cuts, or is it more of a redistribution of funds?
It's a combination of both, as near as I can tell. It's hard to tell where all the cuts are going without seeing details of the DARPA budget, the NIH budget. This is many different agencies across the government. It looks like it is a combination of both reducing funding, because there's so many things that were science funding that led to science education as a broader impact of the grants. That money can't be recouped. So you have, in some cases, a redistribution of the money where it's getting lumped into education, NSF, and Smithsonian, and in other cases where it's just going away.
So are you and other programs like yours aware if you kind of get a piece of that redistributed money, or is all that kind of up in the air right now?
As far as we know, it's going to those agencies, and those agencies will either have to put out new grant calls or will distribute the funding through other mechanisms that no one knows what are. What we do know is this will lead, at a minimum, should it get passed by Congress, which it hasn't been yet, but should these changes get passed by Congress, there will be a large funding gap, for the very simple reason that it takes time to put out calls for grants, for people to write those grant applications, for those to then go through the peer review system. In general, if you put out a call for proposals, there's at least a 90-day window for people to answer that call for proposals. It typically takes 6 months to get the results of that proposal back to find out if you're getting money or you're not. And once you get that result back, it can be another 3 months before you have the check in hand and processed through your university.
So even if you end up with a grant, there's still that period between that needs to be covered.
Right. And a university can't bridge someone for that long necessarily, especially when we don't even know what might be coming. If this all starts in fiscal year 14, we're being told we have to phase out our budgets, but we don't know what they're being asked to phase in. And at least with the Smithsonian, they haven't been a granting agency in the past. So how are they going to handle doing the science outreach moving forward? There's a lot of questions, and there are a lot of people that are looking for jobs, and there just aren't jobs anymore. And this is taking some of our brightest minds who have focused their careers on learning how to educate that next generation most effectively, and telling those people, we're sorry, you're done now.
You're listening to Skeptically Speaking with Rochelle Saunders. We're speaking with Dr. Pamela Gay about the incoming government funding cuts and their effect on education science programs in the U.S. So in addition to these federal cuts, it also seems, sort of heaping bad news on top of potential bad news, that your university is also looking to make its own cuts as well.
Yes. Here in the state of Illinois, our state government has run a severe deficit such that if you take the deficit of the state and divide it by the population of the state, the individual amount of debt is greater for most of the state than the average income. There's exceptions in the richer areas around Chicago, but for most of our state, there's no way the tax base can support the amount of debt burden that's been taken on. Our state isn't able to pay all of its debts in terms of health care, so that when you go to the doctor and they find out you have the state HealthLink health insurance, they often ask you to prepay now because they know it will be 16 months before they necessarily get reimbursed. At a university, they can't wait any more than the doctor's office can wait for those late payments to come from the state. We've had to do that waiting in past years. We've had semesters where we've had to frankly tell our students we don't know if the university will stay open for the entirety of this semester. This year it's reached the point where the university has cut enough of its programs that we haven't had to tell our students that, but we are currently going through a funding exercise where we've been asked to figure out how to cut 25% of our budgets across 3 years. And this is after we've already cut all non-essential services. Part of this means there's going to be no new hires, that when we get grant money, we have to use the grant money for existing staff. And this makes it very hard to grow, very hard to thrive, and hard to provide our students with a cutting-edge education and research experience.
So what do all of these various cuts from all sorts of directions mean for your program?
It potentially means that even though we have devised a way that allows our science team to do incredible science at significantly lower prices to what they would have to look for if they looked for grant money to fund everything being done by the citizen scientists, to have that instead done by students or by themselves. Even though we've developed a way of doing science that is cheaper and that educates people along the way, we potentially go away fiscal year 14.
How many sources of educational science funding are there out there? Are there other sources you can turn to that aren't government-based?
That's what I'm working to do. Part of the problem that we're facing is this came out of nowhere. I thought my funding was secure. I thought I had enough money that I needed to worry about one of my staff members starting in June, but I was pretty sure where that money was coming from. And I had a year and a half to go. And a year and a half to go is plenty of time to find the money that we need. The issue is this came out of nowhere, and we've missed some of the grant calls I would have applied for if I knew I needed to. Again, it's that 1 year ramp up when you apply for money. There are programs out there I'll be looking to apply. Many of them are invitation only, though, and where all of us are going to be going to them. It's going to be a challenging year. We are looking to do crowdsourcing, and we are going to be running at the end of June a 24-hour webathon to try and raise money by spending 24 hours being silly and wonderful and scientific online. And we're hoping that that will encourage people to believe in what we're doing. And, well, if you don't agree with your tax dollars not going to projects like ours, maybe you can spend part of your tax refund supporting programs like ours.
So your current strategy, you talked a little bit about your funding levels. I'm assuming you guys are also looking to trim any what little fat you have on your program to keep things up and running while you're searching for new funding as well.
Yeah, I actually had to make the call that I canceled the student internship that I had. So the student I would have normally hired to work for me for 3 months has to find a new job. I hated to do that, but it was something that had to be done. And where I would normally be hiring a computer science undergrad during the school year, I'm not doing that. Trips that normally would be 2 of us going so that we could take turns doing science demonstrations, it's only going to be 1 person now. So we are basically doing the standard American double the workload, half the staff, and keep running as fast as we can while trying to succeed.
So what can our listeners do to help?
The 3 big things that you can do are write your, I heard them referred to as Congress critters on Twitter today, write your congressmen, your legislators, your representatives. Tell them that you want your science education to be kept in the agencies that are also doing the science, so that today's latest innovations can also go out, not just to other scientists, but go out to school children and the public through science education that comes from NASA, comes from NIH, comes from all the different places that are currently doing such powerful science education. The second thing you can do is look at what are the programs you love? How are they funded? If you love them and they're funded by NASA, figure out if you can donate to keep them alive. It's not just our program. Programs like Astronomy Picture of the Day, Solar System Ambassadors, the Night Sky Network, everything that has NASA funding, we don't know what our future is. And if you can donate to help us bridge the gap that may be coming, well, you can get a tax donation and you can help save the future. And the third thing you can do is make sure people are aware of what's going on. I saw on Twitter the other day people basically squeeing with joy that the Obama administration had given more money for STEM education. And I wanted to cry at the reality, because what is being portrayed, yes, the Department of Education is getting more money, but the cost is great. We need to keep the scientists and the science educators talking together. And we need to keep allowing, well, people like me and so many others who are both scientists and communicators We need to keep them alive, too.
Pamela, thank you so much for being here, and good luck with your funding search to keep CosmoQuest alive.
Thank you so much.
If you want to learn more about Pamela Gay, you can find her blogging at starstrider.com or visit astronomycast.com to download episodes of her podcast. To learn more about CosmoQuest and citizen science, visit cosmoquest.org. And, of course, as always, all of these links will be available in our show notes on skepticallyspeaking.com. And while you're visiting our website, please do click the links to our Twitter feed, Facebook page, and Google Plus page, where you can keep up with the latest news from the Skeptically Speaking team and join in the conversation. You can also check out Skeptically Speaking on iTunes, where you can download all our past episodes and subscribe to get all our future shows. Thanks for listening, and see you next time on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.